Hi guys, so today we are going to discuss about quantum computing. What is a quantum computing? What are its different concepts, and how does this term quantum computing exist? And we will be going to break down all the things in quantum computing, and I will make you understand all that things that are there. So after watching this video, you will get imagination what is a quantum computing, how it works, which machines are used while performing the quantum computing, and what is the scope of quantum computing in the coming future. So I have found this PDF for you from a very known website, and it's very, I have read it and it's very interesting PDF, and I want to make you read and make you understand what is a quantum computing. So let's start with the introduction part. So here they have given some remarks, like after some remarks on the fundamental physical nature of information, Barnett and Franklin ideas of reversible computation are introduced. Means quantum means they have introduced the process of reversible computation. Like if you have computed something on your simple PC, normal PC that we use in our homes, in our offices, if you get result from that, and is there any way you can go back to or its original form from where it started and where it gave the output? So the quantum computing is basically on the idea of reverse computation, and this leads to an suggestion of Benioff and Freeman as the possibility of new type of essentially quantum computers. If we can build such devices, future shows that quantum parallelism means there are different computation are going on in the quantum computing. Means if you have a normal computer, and what is there is a RAM, there is a CPU, and in CPU there is computation in series. They are waiting to get completed, uh, for the thing that is on the first number. Means uh, there is a law in processes, like first come first serve. If some tasks is coming first, then it will serve their task, and after that the second number task a turn is there. So but in quantum computing this thing didn't work. In quantum computing what works is it it gives all the powers, and it work on parallel levels. Like if you have something to calculate, like if you have to predict something, like if you throw a coin in a air, and if you want to predict what will be the head, tail, there are two possibilities, and one very small possibility of that the coin that we have tossed is will remain standby, no, neither head or neither tail. In that case, what quantum computers does, that it calculate the things on parallel levels. Like if there will how much probability is there of coming head, and how much probability is there of coming tails, and how much probability of there on coming standby position, means no head and tail, and what are the environmental factors, in which environment it is performed, and different means it thinks in parallel dimensions to calculate a single thing. So in this parallel computing, we get more accuracy, more accurate result than the simple computers. So yes, the new businesses and the latest generation businesses, which have what do you say which have funds to buy the quantum computers, are uh, buying and using its benefits. And let's read further. So does it show that quantum parallelism leads to new algorithms and new complexity classes? This is dramatically illustrated by Shor's quantum algorithm for factorization, which is polynomial in time, in contrast of algorithms for factorization on classical Turing computer. This discovery has potentially important implications for the security of many modern chirographic systems. The fundamentals of quantum computing are introduced: reversible logic gates, qubits, and quantum resistors. The key quantum property of entanglement is described with due homage to Einstein and Bell. As an illustration of a quantum program, Grover's database search algorithm is described in some detail. After all this theory, the status of experimental attempts to build a quantum computer is reviewed. It will become evident that we have a long way to go before we can factorize even a small numbers. Finally, we end with some thoughts about processes of quantum complication, translating a quantum algorithm into actual physical operations on a quantum system, and some comments on prospects for future progress. So here's the first serial number introduction. So let's read it. The fundamental basis of quantum computing is Lander's observations that all the information is ultimately physical system, be it paper or silicon, which brings us to the key point. As far as we today, all the matter is composed of atoms, nuclei, and electrons, and the interaction and time evolutions of atoms are governed by the laws of quantum mechanics. So, quantum mechanics, the quantum physics has taken birth, and after that, the quantum computing. In quantum computing, the quantum mechanics is used. Although the particulars of the quantum world may not seem rapidly appear at first glance, a closer look reveals that the application of quantum mechanics are all around us. For example, as as has been emphasized by Minsky, the very existence of atoms owes everything not to the chaotic uncertainties of classical mechanics but rather to the certainty of quantum mechanics, with the Pauli exclusion principle and well defined and stable atomic energy levels. Indeed, without our quantum understanding of solid state and the band theory of metals, illustration, and semiconductors, the whole of the semiconductor is lecture in this lecture could not have developed. The same can be said about quantum optics and lasers. New industries from optical communications to music and video CDs have their basis in these intrinsically quantum technologies. At bottom, then everything in quantum mechanical and like of Feynman's in Visionary 1959, plenty of room in and at the bottom talk. We can certainly eventually storing bits of information on single atom of electrons, means they are using earlier what they are doing, they were making some very small level chips, very tiny chips, but now what they are doing, they are using atoms to compute things. That is a very very advanced thing. Means if you are making atoms to compute for you using atoms, so that's there they have said that they are using atoms to compute the things, as they are using atoms as a processor. And in quantum computing what is there is there is a small chip, and that small chip is put inside a container, and that container is set in a temperature of 0, that is 0 Kelvin, means the coldest temperature in this universe. At that temperature the computation is done, computation is taken from the quantum computers. because why the reason behind why this temperature is there, why they put this much temperature on that simple, on the small processor, is because the as I have told that the processors work on chips. So now what they have done is they have made the chips to the atoms. So if little bit of energy, that is heat, that is temperature, is there, then the formation of the atoms in that particular metal can be there. So after the formation of metals, if there is a little bit increase of temperature, if the metal get any energy from somewhere, so then the reading that we want it to give to us may not be the accurate reading. So to make it to provide us a accurate and proper reading, we what we do is we put it on the coldest temperature in this universe, that is 0 Kelvin, and in Celsius it's about 2 minus 273 degrees Celsius. So that is a really really cold temperature, maybe the temperature at the space. So we have talked about reverse computing, and our next topic was there about reverse computing. And it's basically the computation. You have gone if you have done other computation to your computer, like you have given some task to your computer, like you have provided some algebra question to your computer and ask it in the VS Code to uh, to solve it, and you have made all the coding, how it will solve it, and you run the uh, terminal. So what will be there, that it will calculate all the zeros and ones, will calculate the things, and they combine the result, and that single result will be get displayed on our screen. In quantum computing, what is there, that the you have computed from what we say you have computed from algebraic equation to some other equation, you will get you have gotten the result. Like if you have to multiply something, you multiply 26 by 27, you will get x result. So in quantum computing there is a term called reversible computing. So what is there in reversible computing is, you have received the x as an answer, as your solution. So we can make that computer to compute us what is the algebraic solution behind this solution, what is the algebraic quotient. So it can go reverse. Going forward is pretty easy. Eh, in I am not making you understand in multiplication, divide, plus, minus thing, but in other terms, like if you have a really if you have a if you go to big companies like Google, Facebook, they have to protect their customers data. So they have to secure their database. So what they do is they secure their databases by using lots of complex password, and to make passwords more complex, they use term called salting, and different things are there, so that if the hackers are there and they want to hack your password, then they may take billions of years to hack that simple password that you have chosen for your uh, Google or Facebook. So in that case, quantum computing is pretty helpful if you want to break that code in just fraction of time, and because it has the power of computing reversibly. it can compute reversibly. So what happens in reversible I have told, and let's go to our next topic. Here are some of the diagrams. So our so what is in simple computers, like you have a PC or laptop, what is there, how the things work at a basic, at a starting level, at a very scratch level. So if you type something on your keyboard, so how your processor get to know that you have typed that things on your keyboard. So how it works is on the basis of that 0 and 1. In simple computers, that there are two uh, terms 0 and 1. They combine this 0 and 1 and make different alphabets, different sentences. And what happens in quantum computing is that work on 0 1 2 means it works on three aspects. So we get the more accuracy while performing any of the tasks in the quantum computers. So here they have told about the diagram, what is there. You may read it, and you may pause your video and you may read it. I have told the things which are written here. So as I have told you, there are different combination to represent A, this combination B, A dash, the different type of combinations there. So here in part third they have told us about quantum complexity. So it's a very complex process, and lots of scientists from early 1950s have started researching about it. Until from then the growth of quantum computing has started, and nowadays it is a very good solution making machine. You can predict future, you can predict temperature, you can predict the soil quality, what type of soil it will get, if this situation, if this environmental situation it will get, and different things, like if there is a if you have to breed different animals, like different mm, different kind of animals, then what kind of breed it will get, and in medical, for different organs, and different medicine making, it is also used, and for it is also used in curation of viruses and make the uh, antivirus and vaccines. So there is a lot of use of quantum computing nowadays in this time. So as I have told you, qubits are the those things, like there is a container in simple computers. 0 and 1 are put in one container to represent a letter, to represent alphabet. There are qubits in the quantum computing. So quantum, like a container, there are qubits terms in quantum computing. So what happens in qubits, like I have told you, 0 oh, 0 1 2. So in simple computers, if you compute something and stop somewhere, and want to find something, and want to find that where it stopped, 0 or 1, then you can easily find where it gets stopped, 0 or 1. Every time you stop, you will get a result 0 or 1. But in quantum computing, what happens is, due to the superpositions positions, you cannot figure out where is the 0 1 2, where is the position of exact number. So they work on superpositioning things. means they are like electrons. Like if you the like you can't predict where is the electron in an atom, like that ways the qubits uh, qubits elements are there. You can't predict where is the number currently in that qubit. It may be anywhere. It may be here and maybe at that other position also. And like that, maybe another thousands and millions positions also at the same time, at the same fraction of second in that qubit. So here are different formulas and different equations to calculate the qubits, to calculate the position of the qubit. You can check, you can pause the video and read the stuff here. So here is our fifth point, the EPR paradox and quantum entanglement. So what is a quantum entanglement? So let's read what is a quantum entanglement. As is well known, Einstein was suspicious and Einstein was suspicious of the possibilities inherited in quantum mechanics. In the famous Bohr-Einstein debate, he tried to unsuccessful to pinpoint an intrinsic condition in quantum theory. The climate of this debate was in formation with Podolsky and Rosen of a situation in which one of the essential particularities of quantum mechanics was exposed. A modern variant of argument of Einstein, Podolsky and Rosen goes as follows. Imagine we have an elementary particle with zero charge. So let's imagine we have a elementary particle with zero charge and spin. Such a neutral point at rest, momentum is conserved in this decay. Means you have a particle zero charge and spin, it's spinning. Such a neutral pion at a rest, which then at a rest here is which then disintegrates into spin half an electron and spin half positron. Means it have two elements, half is electron and half is positron. As it has shown us in figure 8. So here is our figure 8. So here what he is saying that half of the spin is here in negative direction and half of the spin is here in positive direction. So means electron is moving, but it is also not moving due to the cancellation of positive and negative charges. It is remaining at a still point. So here is the formula, is the sign for, is a Srigunder sign. Srigunder has given this sign and it's called psi, as we have read in our non-medical section of n+1 and n+2 in high school. So here's the equation for psi, for the spin of an electron, for the spin of an positron and electron. So what is the problem? Well, the electron and positron are separately repelled in opposite direction, conservation of linear momentum. If we make the first spin momentum of the electron, the positron, whether in the spin, has to be up or down. In fact, no matter what we do, we always find perfect anti-correlation between the spins, even though there could have been no physical communication between the two particles. Einstein thought that this demonstrated that the spins of the two particles are therefore not intermediate before measurement, but are actually elements of physical reality. According to Bohr's Confagan interpretation of quantum mechanics, it is meaningless to talk of the spin directions of the particles until you make a measurement. This is the truly startling point about quantum mechanics. Orthodoxy has it that there is no object reality, a reality dependent on an observer. For the electrons and their spins, Einstein would have known none of this, thought that things must really be predetermined in advance of the measurement. In other words, although our present formulation of quantum mechanics has the spins as only having a problematic value, and since spooky faster than light signaling is out of the question, there must be some of the hidden variables that make the directions of the spin predetermined from the outside. After several months of the fantastic activity devising a response to Einstein's chance, Bohr declared the EPR paradox not to the paradox at all. They argued essentially at the quantum mechanics demands that you are only allowed to treat the electron position system as single quantum system, and there the matter is arrested as the rather abstract of philosophical debate about hidden variables and objectives reality, since neither side denied that quantum mechanics work as a predictive framework until John Bell entered the debate. So, who was John Bell? Let's read about him. So, John Bell was a great contribution was to deserve a way of putting these two views, hidden variables, objects, reality, and quantum mechanics, not objective reality, to the experimental test. In our discussion above, we have only discussed the measuring spins in up and down directions. What happens if we measure up and down for electrons, but right left for positrons? This is easy to calculate according to quantum mechanics. If the electron is found to up and positron state must be down for our zero spin initial state and stay, and by the standard quantum mechanics of a down state by written as equal superposition of the left and right and states. Thus the measurement of the right and left kind of positron will be yield. So here are the things that is written, so you can read what John Bell has said. And let's move to the next topic. Here's the formula for that John Bell has corrected, and it's the corrected statement for corrected equation of corrected formula that John Bell has provided to us. And here you can read, and pause the video and read the stuff here. So our sixth point is Grover's search algorithm, an example of a quantum algorithm. So here is the Grover's search algorithm, an example of a quantum algorithm. So here the Grovers had told about the stuff about quantum computing. Here's the formula they have given, and you can read here by pausing the video and see this equation what Grovers has given to us. And uh, he have given a formula and equations to calculate the things on quantum level. There is a representation of amplitude and operators for N8 and N3 cover research. So what are the positions of that qubits, how it is calculating things inside it, and what are the position and 8 position and 8 shell, it is giving the result for that. It is a diagram how it will if any of the position get disturbed, then what will happen in that position. So here all the things are written and you can find the things, um, and if you want to read, and you can pause the video and read it. After that we have the things is experimental quantum computer state of the art. So here they have done some of the experiments with quantum computing and developed a very good computer at a starting stage. And here they have given conclusion what we have read in the what we have read in above sections. So that's all for this video, and I'll be coming up in our next videos to make you understand about different other concepts. Till then, have a nice day. Bye bye.